Hi, I'm Puyan Lotfi, and today I'll be talking about MIR-Canon. The first question many of you may have is, what is MIR? Well, MIR is the newer serializable and deserializable machine IR for machine insters, and it looks something like this. Looks somewhere in between LLVM IR and the machine inster print output. I'm sure many of you have seen this before. And so the next question you all may have is, what is MIR-Canon? Well, MIR-Canon is a newer machine pass built with the aim of doing canonical transformations on MIR code that canonicalize register naming and instruction placement for a given MIR file. And the goal is that for two similar programs, two similar MIR files, MIR-Canon would have, after processing each of them with MIR-Canon, the semantic differences would stand out over the non-semantic differences when loading them in a diff tool. So you load up your diff tool and the real meaningful differences pop out at you, and the other stuff sort of fades to the background. So a really common workflow I'm sure many of you have seen is you're diffing IR or MIR or assembly, and you see a whole lot of red here. This is Vim diff. And a lot of you may spend hours or quite some time reasoning through this to try to semantically alter the register operands and the instruction placement so that you have a cleaner diff, just so you can figure out what really is different here. And a lot of this is just an artifact of register naming differences cascading down through a number of different instructions, causing a whole lot of red here. And a more ideal situation is, let's say you have two compiler pipelines and you want to diff the results, and maybe one optimization is enabled versus not enabled on the other one. And sometimes you just get lucky and your diff ends up looking like this, where you see exactly what you want in terms of what's different. And in this case, on the right hand, you've got a move, in case you can't see it, it's a move I64im, and on the left side, there's a move I32im, and because of that, it needs to be extended with a subreg to reg. And here it's very apparent. And the goal of MIR-Canon is to arrive at this diff. Before I go any further, I'd just like to point out this is how you'd invoke MIR-Canon. It's just a -run pass MIR-Canonicalizer on LLC, so let's get into it. So what were the reasons for building MIR-Canon? Well, the two major ones were to improve the state of code diff and code verification for MIR code, and that means we need to preserve the semantics, and so therefore that means we can't just do trivial sorting and renaming of operands to some dummy operand. I've seen a lot of simple scripts that just take some assembly or some MIR, sort the instructions, and then rename all the VREGs to like some dummy value. That's not good enough. We want to have a really solid semantic diff here. And one of the major assumptions we made is that any MIR that we want to diff is going to probably originate from the same source IR, and we're just diffing some slight discrepancy in two compiler pipelines, and we want to explore that. And our initial primary application for this project was to compare and verify GlobalISel versus SelectionDAG code gen output. And some early considerations we made were that we don't want to create yet another diff tool. We want to, in fact, leverage existing diff tools, because there's a whole lot of really good diff tools out there. Some of them cost a good amount of money, but there already exists really good textual diffing tools, so we don't want to reinvent that. So because of that, we limited ourselves to analyzing one file at a time, and so we implemented MIR-Canon as a generic machine pass. And some other ideas that we considered were can we use the def use graph as a way to basically arrive at a canonical transformation while still adhering to proper semantics? And lastly, are there situations where we could sort chunks or groups of instructions alphabetically so that we have a more, basically a diff that lines up more nicely because things are sorted alphabetically on both sides? So if we want to get to a more canonical form, say for this MIR, this MIR stream of MIR code is actually what we saw in the previous Vim diff. And how do we get to what we see here on the right? Clearly, it looks a lot neater. The instructions are all named name vreg and then some number. They're all monotonically increasing. A bunch of instructions are sort of hoisted to the top and sorted. Overall, this looks neater, and we think that this kind of, whatever this transformation is doing, which is what MIR-Canon does, will lead to more often than not having cleaner diffs of MIR code. How do we arrive to this? Well, so some of the algorithmic details here, we have three major techniques. One is virtual register renaming, and then we have instruction reordering, and finally code folding. And all three of these in this iteration of MIR-Canon were designed to be ISA agnostic, meaning that we don't really query the target for any machine-specific info in any of our canonicalization, but we also don't really make sense of any opcodes. We don't use the opcodes to canonicalize in this iteration of MIR-Canon. And lastly, all of these techniques are local only, so we only apply them on a per basic block basis. But we do process all the basic blocks in a CFG in a reverse post-ordering, and this gives us sort of a canonical ordering of the basic blocks. So the first major technique I'll get into is the def use walk virtual register renaming scheme, and I would say this is like the major backbone of MIR-Canon. So the way this works is that for a given basic block that we're processing, we scan the basic block for side effects, and these side effects can be either writes to physical registers or stores to memory. And for each of these side effects, we process them in a bottom-up ordering based on where they're placed in the basic block. And then for each side effect that we process, we walk the def use graph routing from that side effect. And as we walk up, we generate new names for the VREGs as we encounter them. And the high-level goal is to allow for the shape of a def use chain to determine the shape and placement of a def use chain stemming from a side effect to dictate the new names for the VREGs in the program. So for this stream of instructions that we see here on the left, we identify the side affecting instructions, and those are these 5 stores, and then at the bottom we've got a copy to physical register X0. And once we identify them, we collect them, and we process them in a bottom-up order. And then for just one of these, so for this store DUI, we do a walk, and this stream of instructions are all of the instructions that we encounter in the walk of the def use graph within the current basic block, because we don't go outside of the current basic block. And as we walk the def use graph, one of the mechanisms we use to effectively keep state is this VREG number cursor. And the VREG number cursor both keeps the state of the current number for the VREG. And this number isn't the actual VREG value, it's just a number that we use as part of a string to rename the VREG. And the idea is when we instantiate this cursor, we skip a whole bunch of numbers. Basically, we initially call create incomplete virtual register to get an idea of how many VREGs are allocated in this MIR program, and then we use that to skip a number modulo m. Basically, we're rounding up to the next however amount, like in the case right now, normally we round up to the next 1,000th number, and then we use that number. The idea is that for two MIR files, we should round up to the same place, and then from there we can walk, and we should land on the same numbers for two different MIR files. And that way we can rename canonically. And so as we do the walk, we create new VREG names, and we rename the VREGs. And for each walk, we actually skip a little bit as well. So we round up for every walk. At the beginning of the program, we round up a lot, and then at every walk, we round up a little bit. And we basically do our walk, and we rename the VREGs in the def use graph. And the idea is that for two different MIR files, when we encounter a def use graph in each in the same place with the same topology, we should be able to walk the def use graph and rename all the VREGs in the def use graph the same way. And so this VREG renaming technique, it works because we walk over the basic blocks in a canonical ordering, and then we walk over the side effects in a canonical ordering, and then for each side effect, we do a walk of the def use graph, and we rename. The two major assumptions made here is that two similar programs, if they're semantically similar, they should have roughly the same side effects in roughly the same places, because, I mean, you know, they're stores to memory. If they mean the same thing, probably their stores are lining up in roughly the same way. And also that the CFGs are probably roughly the same, if not identical. And in the case of diffing GlobalISel versus SelectionDAG ISel, this has been pretty effective. It's been a pretty decent assumption. And so this is what we had before. And after, just with the VREG renaming technique that I explained, we have a much cleaner diff here, a lot less red. So now I will get into the instruction reordering techniques. And so the first one I'll get into is the def use distance reduction technique. And in def use distance reduction, when we have multiple defs that flow into a common user, we try to move those defs closer to the user. And the idea is that these defs, they only need to be just before the user for semantics to be preserved. And otherwise, they could be interspersed anywhere in the basic block. And by moving them closer, we're limiting the amount of variation that could exist, thereby reducing the difference between two MIR files if we move them all to the same place. And so the way it works is we've got this stream of instructions here. We identify two defs here that flow into this reg sequence, and then what we do is we just move the defs down and we sort them, and we also rename the dest operands. And so the before and after is that before, these defs are interspersed in any old place within the basic block, and after, they're just right before the user. Next is independent instruction hoisting. And the concept of independent instructions that I thought of was instructions that don't read from any VREGs, but they write to a VREG. And these are things that they're reading from an immediate, or they're reading from a physical register that isn't written to anywhere in the basic block. And the idea is they could be placed anywhere in the basic block just as long as they're before the first user. And it's best to move them all to the same place rather than having them interspersed anywhere that they're already placed. And so I try to move them all into the same place and sort them. And the most convenient place is to move them to the top of the basic block. And so you have these independent instructions like these move I32ims and these copies from physical registers. And then what independent instruction hoisting does is it collects them and then it inserts them at the top of the basic block, and it sorts them and it renames the dest operands just from the top. And independent instruction hoisting, it works well for cleaning up diffs for two reasons. One is that it's pulling these independent instructions out of code where it could just be causing noise. It's just, they could be interspersed anywhere in the basic block, so naturally they kind of lead to a noisier diff if they're not all moved to the same place. So you're both pulling it out of somewhere where the diff would have been noisier, and you're placing them all in the same place and you're sorting them. So the place where you're sorting them is also diffs a lot more nicely too. And the before and after here is that they're, and this is the same example we had previously at the beginning of the slide, where we've got these independent instructions, they're interspersed all over this basic block, and after they're moved all to the top. And lastly is copy folding. This is the only folding technique that I've thought of so far. And this is just, basically, this is a ISA agnostic folding of a copy. Basically the dest and the source and the dest have to both be VREGs, and they both have to be the same register class. And if that's the case, then I fold the copy and I rewrite all the places that it was used. That's the before and after. And now that we've gone over copy folding and all of the instruction reordering techniques, this is what we had just with the VREG walk technique for renaming the VREGs, the def use walk technique. And this is after. This is with all of the other techniques applied. So we've arrived at where we were in the original example. So the usage of LLVM that I made was mainly, I implemented all of this with a machine function pass, relied really heavily on SSA for the def use walk and for the def use distance reduction. And I added named VREGs to MIR just as a way to better rename the VREGs, and also there are some future techniques that I will go into in a couple upcoming slides on better ways to rename the VREGs. And so the usage for MIR-Canon, the most straightforward usage is that you have your the two cases that you want to compare. In our case, DAG-ISel versus GlobalISel. You pipe the output through the MIR Canonicalizer, and then you just diff the results. But another idea I had that actually kind of works fairly well is you canonicalize the two, and then you run diff. And then I wrote this little script called scrape diff, and what this does is it pulls artifacts out of diff, mainly the opcodes that are different, and then I just hash the results. And so for this diff that we had in the beginning, the scrape diff output would be the sorted opcodes that were different on the left versus the sorted opcodes that were different on the right. And then hashing that would give you this MD5 checksum. And what I ended up doing was running this on our entire test suite. And this was pretty effective at giving like a frequency count of different diffs across a wide set of programs across the test suite. And this was really possible just because MIR-Canon is really making the real semantic diffs stand out and causing all of the other diffs to sort of fade back. And we've been using this to direct our work on what to implement next with GlobalISel and some other things. So I'd like to get a little bit into future work. The first item of for future versions of MIR-Canon I'd like to explore is implementing a symbolic VREG renaming strategy. And so looking at this diff again, I don't know if you guys can see that, but we have, other than the main diff, we have some of these off by one VREG differences, and this is because we're using a numbering VREG renaming scheme, and because we have this subreg to reg here, then the next VREGs are sort of off by one compared to this side of the diff, and the VREG numbering cursor is not always smart enough to be able to overcome that. And I think if we had a symbolic VREG renaming, a symbolic naming scheme where I can imagine maybe for a given def use graph, the names of the VREGs would be either based on the opcodes encountered in the def use graph, or maybe they'd be hashes of the opcodes or something like that. I think that could be more effective than just having named VREG and then a number. Oh, right, I meant to point out that these are all the different VREG numbers that are sort of off by one. And just to prove my point, I went in and with the original example where the two are very different and you see all the red, I just fixed just the part where it was move im I32 to move im I64 and remove the subreg to reg, and MIR-Canon just completely wipes out this whole thing. It's completely, there's no diffs anymore at all. And also the off by one differences are gone as well. The other items for future work are exploring ISO-specific canonicalization techniques. Here I can think of two examples. So for the copy folding, I'm limited to copies to and from VREGs of an identical register class. But if I could query, when I start querying the actual target info, I could probably expand that to cases where the register classes aren't the same, but it's still legal to fold. Another kind of type of ISO-specific canonicalization is, I could imagine maybe querying some of the table gen information for patterns that are identical and always replacing them with instruction patterns with the same instruction pattern. So for example, on ARM64, if you want to zero out a VREG, you could always copy from this 0 register, or you could move im0. Ideally, you'd want to identify all of the different types of ways. For this use case, you would want to identify all the different types of ways to zero a register and always replace them with the same canonical zeroing out of a VREG. And then the next technique, the next item for future work I've been thinking of is exploring global canonicalization techniques. So the simplest one I can think of is for, like, in the case of the independent instruction hoisting, rather than always trying to hoist to the top of the current basic block, maybe hoisting to the top of the entry basic block. I think that would actually work really well for comparing GlobalISel and DAG-ISel, because I believe GlobalISel actually sticks a lot of its immediate population in the entry basic block. Also, I think there's potential for doing the def use virtual register renaming walk across basic blocks, but I just haven't thought about it a whole lot yet. And lastly, code gen hardening, I think, is an area that could have a lot of corner cases. So far, I've only been testing this in the context of diffing two MIR files, but not necessarily testing out the the actual code that gets generated. I think it could be possible that MIR-Canon would be used as a pre-pass for other optimizations, like say outlining. I could really see like having a bunch of code being canonicalized and then the outliner being able to match more cases where things could be outlined out to functions. I think that could be useful. Finally, all of this is currently in top of tree LLVM. All of the code is contained in libcodegen MIR Canonicalizer pass.cpp, and it's ready to use with lc-run pass MIR Canonicalizer. And I'd like to open it up for questions. Thank you for coming to my talk. Oh, you. Thanks. You.
So my initial question is it possible to port that to LLVM IR?
It should be. I don't see why not, because it's very VREG and SSA driven. The reason I wrote it in MIR was to test instruction selection in the initial version. There's also, you might also want to look at LLVM diff. It actually does this sort of opposite approach where it tries to compare two IR files, so you could look at that as well. But there's no reason that a lot of this stuff couldn't be ported to LLVM IR. That's true.
Can I have a second question?
Yeah, sure.
Okay, so have you considered that a special option would be that I choose a variable and the canonicalizer filters out anything that doesn't influence given variable? Because normally when I am checking diffs, it is possible that I have some change and it causes a lot of differences in code, but those are good differences. And normally I would check some variable that I suspect might be wrong.
So having a bunch of knobs that let you control what kind of things it does. So you, I've thought a little bit of that, but I've been mostly just trying to get all of these techniques working together in the first version. But that's that's really good.
That's a great start.
Yeah.
Thank you very much for good talk.
Yeah. And if you could ping me about any features in that area you'd like, that would be good. Okay. Oh.
So in your code, some instructions may have side effects. Like, what if you have like a call to some other function in your basic block? Then some of the moves you're making are no longer legal.
Right. So that's sort of an area I would want to explore with code gen hardening and sort of tightening up some of how I consider what's semantically correct. But I think a lot of function calls, they end up being like setting up, or at least in ARM64, as I can see in the MIR, it's writing to a physical register before, like as part of the calling convention. Yeah. And so I use those as sort of the root for the side effect and do the walk.
Can I have also a second question?
Yeah, sure.
Yeah, and when at what point, after which passes or before which passes do you run? Like
So right now, MIR-Canon could just be invoked anywhere between post-instruction selection and wherever we're still in SSA form before things become de-SSA'd. I think there are still some issues in some of the later stages of the pipeline, but using it on MIR that comes straight out of instruction selection seems to work pretty good right
Thank
now.
You.
Yeah.
Any other questions? So let's thank the speaker once again. Thank you.
Thank you.